Hello everyone, today let's take a look at a path problem, quantipus number 31. The setup is a person's workplace lies 7 blocks east and 8 blocks north of their home in Manhattan. So in how many distinct 15 block routes can they walk from home to work? So this is what I drew to model the problem. I have the home over here and work over here. You can see it's 7 blocks to the right and 8 blocks up. And now that I'm looking at it, it almost looks like an optical illusion. The dots are kind of flashing black and white, so I'm sorry about that. So one thing to note when solving this problem is that we are looking at 15 block routes exclusively. And since we have to walk 7 blocks east and 8 blocks north, so 15 blocks to get to work, we are not going to be able to walk south or west without not being able to make it there in 15 blocks, if you know what I mean. So this right here is a valid route. Maybe we just go like this. And then this right here is a valid route. This one will also be a valid route, and we just need to count the number of routes that there are. So you can see that every path that starts at home and ends at work within this grid is going to be 15 blocks long. So we just need to count the total number of paths that start here and end here and are in this grid. Now this setup right here is going to be the key to solving most of these path problems, where we're going to think of a path as just some combination of e's and n's, where e represents east and n represents north, obviously. So for instance, this path right here would be 7 east followed by 8 north. So that would just represent this path where we go east 7 times and then north 8 times. And then for instance, if we switch, let's say this n and this e right here, well then this would represent the path where we go east 6 times first, and then we go up 1, and then we go east another, and then we go up the remaining of the way. Now just one more example, if I alternated east and north, let's say, it would look something like this. This would be right here in blue. So now you can see the way that we can solve this problem is just by counting the number of ways to arrange 7 e's and 8 n's in a sequence. So this is just a multinomial problem, right? I have 15 items to place in 15 spots, 15 factorial ways to do so, but these e's and n's are indistinguishable relative to each other, right? So I need to divide by the number of e's in a factorial, so 7 factorial, and then you divide by the number of n's in a sequence, so 8 factorial. And another way to think about this is I'm just going to choose 7 out of these 15 spots to be my e's, and then I'm just going to fill in the remaining 8 with n's, and that's just going to end up equaling 15 choose 7, and what do you know? This is also equal to this. I could have also thought let's just choose 8 of these spots to be my n's and fill in the remainder with e's, and that's just going to be 15 choose 8, which we know is equal to 15 choose 7, which is equal to this, right? So you can think about it any of these ways, but it's going to end up equaling this right here, which is equal to 6,435 once you do it out, and that is the final answer. Hello everyone, today let's take a look at quantipus number 33, which is another path problem and a complete follow-up to quantipus number 31, so do that one first. So let's use the streets from this problem, and let's denote the north and south ones by A, B, C all the way to H, and the east and west ones by 1st Street, 2nd Street all the way up to 9th Street. So let's just take the exact same diagram from quantipus 31 to illustrate this. So the north and south streets, right, the ones that go up and down, are going to be denoted by A, B, C all the way up to H. Now let's do our east and west streets, the ones going side to side, as 1st, 2nd, 3rd, 4th, all the way up to 9th Street. Now the difference between quantipus 31 and this problem is that East Street between 5th and 6th is going to be shut down. So let's find that. This is going to be East Street right here. This is going to be 5th Street, and this is going to be 6th Street. So that means that this street right here is no longer walkable, and now we need to calculate the number of ways to get from here to here given this. So the strategy to solve this should be, let's calculate the total number of ways to get from here to here, which we did in quantipus number 31, given that there is no restriction. So let's do that first, and we got 15 choose 7. And this ended up being equal to 6,435. And then let's just subtract off the routes that go through this invalid street here. So how do we calculate this? Well, we know that any path that passes through the invalid street is going to, at some point, end up right here. And we know that once we're at that point, we can either go this way or this way through the invalid street. So let's just subtract off the number of paths that get to this point right here and then go up through the invalid street. So this is essentially what we are calculating right down here, right? Let me zoom in. Let's just calculate the number of paths through here, and then this is going to be our invalid count because every single path through here must go through this invalid street. So what we need to do is just calculate the number of paths to this mini subgrid and then multiply it by the number of paths to this top grid. And we're going to do this because for every single route through this bottom subgrid, for instance, this one or this one, we're going to have exactly one way to get to the top grid. So for every single one of these subroutes, we're going to get to this point, and then we need to calculate the number of routes from this point to the final destination. So we're going to multiply these. So first, let's calculate it for the bottom grid. We know how to do this from quantipus number 31. We need to go 4 times east and then 4 times north to get to this point in any arrangement. It's a multinomial problem. It's going to be 8 factorial on the number of e's, which is 4 factorial, and the number of n's, which is also 4 factorial. And this is also just equivalent to 8 choose 4. We're choosing 4 different places for the e's or the n's out of 8. And now for the top part, it's also going to be the same story, right? We have 1, 2, 3, 4, 5, 6 places, and we're going to end up dividing it by 3 factorial, 3 factorial. So this is also 6 choose 3 by the same logic as down here. So for the number of invalid routes, we're going to have 6 choose 3 times 8 choose 4. This is 20 and this is 70. So when we multiply them together, we're going to get 1400. And then when we end up subtracting 1400 from our total, we're going to plug in 1400 here, right? So once we plug in 1400 here, once we do the subtraction, we're going to end up getting 5035, which will be our final answer.